All right. Welcome back, everyone. As I said, the second homework is out. The first project is also out. The project is a great way for you to kind of practice the things that we have discussed in the past 2 weeks. Um, so, like, learning about ISA and microarchitecture. Uh, project is very, very good way to kind of go through that process yourself because you will learn kind of by doing. Uh, Essentially, the idea of the project is that we want you to code the design that we went over last week, based on the instruction and the kind of the ISA and the machine code that we described the week before. So in the process of doing that, you will learn how to kind of like how the machine code works and what are those kind of different parts of the instruction. And then you will also learn about all those different units inside the data path. And then another good thing about the project is that not only you will learn kind of like the high level idea, you also need to go to the nitty gritty and details of implementing the ALU and the register file and all those things. So it's kind of like, think about it as kind of like a way for you to prepare for your quiz and learning about the course itself. So it's really kind of goes hand in hand, I would say. So don't like kind of like try to first read the lectures and understand the lecture by watching videos and looking at the slides. But a great way to practice for that would be doing the project. Okay. Anyone has already started doing the project? Well, yeah. So it's due next Sunday. So yeah, the due date is for it's set such that it's just overlaps with your exam, which would be the following Tuesday. So that's why I won't be able to extend it. Just keep in mind, because again, I want you to do it before the exam, which is Tuesday. Okay, so far we have kind of like we went over this design. We talked about different parts of this, and as you kind of like repeat this process for yourself of watching and rewatching the lectures and all, you probably like learn more about every single detail in this design. And then we kind of like second half of previous lecture was about, okay, is this efficient enough and is this fast enough? And we said that it's very simple, but unfortunately it's not the greatest way of implementing that. The reason for it was that the path that takes for the instruction sometimes is like really long, especially for things like memory. And the problem with the single cycle is that every instruction needs to be abiding by that timing, which means that we are kind of designing our system for worst case scenario rather than for the best case scenario. And then we kind of like try to also kind of systematically measure the performance, and we went over this, what we call the iron law of performance processor, which was kind of like there were 3 parameters, each of which has direct impact on the CPU time. We talked about them, each one of these metrics, like the instruction count, which is not really a hardware component, it's more of like compiler or algorithm. Then cycle per instruction, that's kind of like the main thing when you're designing the processor. And of course, the cycle time, which is kind of like 2 things. One is the technology and the other one is the design. And then we also gave you another way of designing, and that was the multi-cycle. And we said that multi-cycle, good thing about it is that it gives you shorter cycle time because now you kind of isolate each unit from the other, but it doesn't really decrease the cycle per instruction. It actually increases cycle per instruction. And hopefully while you're doing your homework, you will kind of like can actually see the numbers, the exact numbers to learn more about this. All right. And then, yeah, so that's kind of like where we at. So we said that the cycle time goes down, but unfortunately the CPI goes up. And kind of like if you don't do anything else, they cancel each other out. So you're kind of like your multi-cycle performance is not very different than your single cycle performance. All right. So let's talk about what we can do in order to make this better, so make this faster. And this is the idea of parallelizing or pipelining, okay? So the pipelining design is kind of like, the book is using this analogy of laundering. And I'm going to use the same idea. So think about like, your laundry as a 4-step process that you wash, you dry, you fold, and then you put it into some form of closet, right? And think about this as 4 different steps, as similar to the 4 different steps of a process or pipeline. Okay. In single cycle, let's say you do everything in 30 minutes. So let's say 30 minutes takes for washing, 30 minutes for drying, 30 minutes for folding, and 30 minutes for kind of making things nice and tidy. And if I have a bunch of these loads, let's say you have 4 different roommates in your building or in your house. So if one of you wants to do this, we can do this way, as in the first person goes through the whole process, and then the second person goes through the whole process, and the 4th person goes through the full process, right? So this way, if everything takes, like if one process takes 2 hours, the whole process takes 8 hours, okay? But then obviously there is like a very obvious and very intuitive way to parallelize this process, right? The parallelizing the process is that essentially assuming that each of these units are independent from the other, right? So what we can do is that if person A starts using the washer, as their load finishes and they start using the dryer, the next person can start using the washer, right? Because the washer is empty now. There's no need to wait for the whole process to end for you to start using the washer, right? So essentially what will happen is that during this time, the second period, now we have some form of an overlap. The overlap happens in time, but not during the resources. We still have just one washer and one dryer, and let's say we can only like fold one at a time, and we have one closet at a time that we can put the clothes in. But since now they can be happen in parallel, there will be a time that all 4 units can be used at the same time, right? So at this moment, all 4 users are using different parts of the system, right? So one is using the washer, the other one is using the dryer, the other one is folding the clothes, and the other one is just putting the clothes in the closet, right? And if you look at the overall end-to-end time, for 4 loads, what used to be ending at 2 a.m. now is ending at 9:30, because now we have like things happening overlap and happening in parallel. We're not changing the hardware at all. We're not buying extra washers or extra dryers, or we are not doing folding multiple times. We are just reusing the resources. So that's the key thing with the pipeline, that we are not doing any sort of parallelism in terms of resources, additional resources, but we reuse the resources that we already have. Later on, we're going to kind of like extend this analogy and say that, okay, what if I have 2 washers? What if I have 2 dryers? What if I can fold clothes 2 at a time, and so on? And that makes this system even faster. But for now, let's say we have only 1 washer, 1 dryer, 1 folding, 1 closet. Still, I can parallelize things this way, okay? So in other words, what we are doing is that we are increasing the throughput. So still, 1 full load takes 2 hours, okay? So we are not really making each individual load or each individual instruction faster. But since I have many loads, I can parallelize this so that, in other words, the entire thing takes less amount of time. So now think about this in the context of program, that I have many instructions. If I can parallelize these instructions, then my entire programs finish faster. So I'm increasing the throughput. By increasing the throughput, I reduce the overall end-to-end latency of my program, okay? But again, I'm not really making one single instruction faster. I'm just making the throughput higher, okay? So that's the story of the pipelining, and then as we kind of like shift back to the design of our processor, here's what we're going to do. If you remember last time I told you that I'm going to show the data path this way. So this is the instruction memory, this is the register, this is the ALU, this is the data memory, and this is the write back when we are writing the data back to the register file and PC, okay? So I'm gonna use this 4 pipeline registers here. These are the buffers that I showed you last time, and you've probably seen it in the homework as well. So I'm creating this 5-stage pipeline. And remember, the reason that we did 5 and not 3 and not 7 was that we wanted to make this equal. So we want to make each stage almost similar amount of time as the others. Otherwise, I'm wasting time. So now what I'm going to do is that I'm going to essentially kind of have overlap. So as you can see here, for example, at this point here, so if I show you the instructions here, so this is instruction number 1, this is instruction number 2, this is instruction number 3, and this is my time. What I'm showing you is that in cycle 1, I'm going to fetch the first instruction, okay? Now in cycle 2, so this will be cycle 2. So at cycle 2, this first instruction goes to the second stage of the pipeline, which is, if you remember, was like reading the register file. As I'm reading the register file for first instruction, I fetch the second instruction, okay? So at this point, I'm doing 2 things at the same time, but they are independent from each other because they are pipelines. So here I'm reading the register file for instruction number 1, but also fetching instruction number 2. And then things kind of go next stage. So now in third cycle, so this will be the third cycle. Now in the third cycle, this instruction that I read from register file is now fed into the ALU operations. So the first instruction is in ALU. Now the second instruction can go to the register file and read the instruction, like, the registers from the register file. So my instruction 2 will be here. And now I can fetch the third instruction. And I can continue this. So at any given point, since I have 5 stages of pipeline, I can technically do 5 things at the same time. So at some point here, I can do reg here and instruction memory here. So at one given time, if I see the cross section of all these things, there are 5 independent instructions inside my processor. So different stages are doing different things. Yeah. You mean like here? Yes. So this one and this one, right? Yeah. So the question is, how can we actually kind of do this thing that now instruction 1 is accessing register file and instruction 4 is also accessing register file. If you remember, my design of register file was multiple ports, right? So it's essentially instruction 4 will be reading, so it's going to use these 2 ports. But my instruction 1 going to write to it, so it's going to use these ports. So these ports are independent from each other. That's the whole point of actually having this port, so that now I can do 2 things. Yeah. Yeah. So the question is that, like, if you are reading and writing to the same register, what will happen? And these are great questions. And that's actually what we're going to discuss in this lecture. Yes. So another question is, what happens if there is a branch? And that's also another problem that we're going to face with this. And we're going to talk about that. Yeah. Same question. Okay. Good that you guys are ahead of the game. All right. So now if you look into kind of like from the outside, so if you look at this, let's say my pipeline is quote unquote filled, so that now I have all the 5 instructions inside. What will happen is that if I see how many instructions do I run per cycle, now the answer will be equal to 1. So essentially, each cycle I finish 1 instruction. If my pipeline is full and I can kind of keep pumping instruction inside my pipeline, then if I look at this last stage, I'll see that at every cycle there is 1 instruction that finishes. Okay? So in other words, I'm reducing my or I'm increasing my IPC instruction per cycle back to 1. Remember, for multi-cycle, or for single cycle, that was 5, right? It takes 5 cycles from this one goes to this one, and this one, and this one, and this one, and then finishes. So we will have, after 5 cycles, we will see this. But since things was sequential, there is another 5 cycle after I see the next instruction, and another 5 cycle after I see the next instruction. That's why my IPC instruction per cycle was 1/5. But now with this way that I'm kind of overlapping things, when my pipeline is filled after 5 cycles, after that, I basically will see that at every cycle there is one instruction that finishes. In other words, at every cycle there is one instruction that is done. So we kind of managed to make the IPC equal to 1. But the beauty of this is that now your cycle time is 1/5 your old cycle time, right? So your single cycle time, because now you're pipelining your system, so you no longer need to wait and measure the whole time. All you need to do measure is that the maximum between times. So in other words, with pipelining, I managed to keep my IPC to 1 per cycle, but my cycle time now is significantly reduced. And as a result, the entire CPU time is divided by 5, which means that now I'm 5 times faster than the design of a single cycle, okay? So by just creating this design and this overlapping, I make the exact same system. So I'm not really introducing new register file or ALU or anything. I just add pipeline registers, and I do this overlapping, and now I'm 5 times faster than a single cycle. Yeah. Yes. Yes. So the question is, like, your IPC is not 1, it's kind of close to 1, it's like 0.99. But yeah, if you have an unlimited number of instructions, then to infinity it becomes 1. So to give you like a more concrete number, let's say, for example, we have a single cycle versus pipeline. Let's say we have load word, store word, R type or R type, and branch equal. And then let's say we have the 5 stages that I said. Let's say your instruction takes 200 picosecond, register file 100, ALU 200, memory 200, register write 100, okay? If I just sum them together, that would be 800, and then 700, 600, 500. If you remember, for the single cycle, right? For single cycle, the CT would be the max of these, right? So the max of total time, which in this case would be equal to 800, right? We have to wait for the longest. And my CPI, or let's say, actually, let's write IPC. My IPC in this case would be 1/5, because every 5 cycles I finish one instruction, right? Now what happens is with pipelining, sorry, so this is single cycle. So my IPC was 1. I made a mistake. So this is a single cycle design. I finish 1 instruction per cycle, so my IPC is equal to 1, right? So that's what I have here. For my pipeline, though, if you look into the pipeline, the way that we're going to calculate the CT would be the max of each stage. And as you can see, for example, these 2 stage or these 3 stage are all 200 picosecond, which means that my CT will be 200 picosecond. But as I said, since I'm now overlapping things, I still have a CPI or IPC equal to 1, but now I have a clock cycle of 200. So my quote-unquote speed up would be the single cycle time, CPU time, sorry, CPU time divided by my pipeline design CPU time, right? And then we're going to use the iron law, right? So the iron law was saying that it was instruction count times CPI times CT, right? And this one is also instruction count, CPI, CT. So if I'm assuming that I'm running the same application that has exactly the same number of instruction counts, these two cancel each other out. I just told you that the CPIs are both equal to 1. And now the CT, this one is 800 picosecond, and this one is 200 picosecond, right? So effectively, what I'm doing here is now I have 4 times faster CPU, 4 times faster design. And that will be basically just the speed up I'm getting purely for pipeline design for this particular system. As I said, ideally, you're probably looking at 5. If you are doing exactly half, as you can see, for example, the reason that I'm not getting 5 is that these two happening faster, so I'm wasting a little bit time, but unfortunately, I cannot do much about that anyway, because that's kind of like the memory is kind of the bottleneck in your design. But you will looking at like somewhere between 3 to 5 times faster design by just doing the pipeline. Does that make sense? Yeah. Can you repeat the question? So the question is difference between single cycle and pipeline. So single cycle, we need to finish the instruction in one cycle, right? And then in order to find how long should be my cycle, I need to find the max time of this, right? So my cycle should be more than 800 picosecond. Okay, that's how I finish this instruction. So every instruction, in other words, takes 800 picosecond. With pipeline, now I'm clocking the system. So I'm adding these registers in between, which means that now I can clock the system faster. I clock the system based on the maximum of per stage. And as you can see in this design, there are 5 different stages. Each one takes somewhere between 200 or 100, okay? So in this case, it means that if I look into this design, I'll see that the fastest that I can clock this system is 200 picosecond because that's the stage that it has. So immediately I change my cycle time from 800 picoseconds to 200 picoseconds. So that's 4 times faster, okay? Now the question is, what is my CPI or IPC? In single cycle, the IPC is equal to 1 because that's the definition of single cycle. I finish an instruction per cycle. So IPC obviously is 1. For pipelining, I'm doing this analogy of loading. So essentially, if I look into the end of the system, at any given cycle, I see that I finish one load, one full load. So in other words, my IPC is also equal to 1. So IPCs are equal to 1. So now that I'm basically just plugging the numbers into my equation. So ICs are the same, CPIs or IPCs are the same. The only difference is the cycle times. One is 800, the other one is 200. That's why I get 4 times faster. Make sense? Cool. So this is kind of the design of my pipeline. As I said, I'm going to call these things. So I'm going to call these 5 stages fetch, instruction fetch. I'm going to call this instruction decode. I'm going to call this execution, call this mem, and then call this last one write back because I'm writing the result back to my register file and to my PC, okay? So now the question is, what should go where? And some of these things are obvious, but some of them are not. So for example, should I move this here? Why I put this one here and why it's not like here? Why, for example, the mux is here and not here, and so on and so forth. The short answer for this is that we make these things so that the design is taking almost equal amount of time for each stage, but we're going to actually go through this process again together so that you will see that how we design these different stages. Question? The question is there any situation that the CPI for the pipeline is not 1? Yes. So if I cannot push one instruction at a time inside, or for some reason the pipeline stops for some reasons, then I cannot have a CPI. So think about, for example, if your dryer break, right? So it doesn't work. Then you cannot no longer like put things into the washer, right? So you need to first fix the dryer and then continue your process. There are a bunch of scenarios that this will happen, and we're going to talk about that. All right. So the first thing I want to talk about is the controller itself, because remember, I'm just showing you the data path. There's nothing about the controller, and we had all those signals. So how do we actually design the controller in this pipeline stage machine? So the controller, if you remember, the controller will be used in the decode stage. So it's somewhere inside between this between these two registers. So this was my fetch, this is my decode, this is my execute, this is my memory, and this is my write back. So my controller gets the information from this IFID register. So it happens during the controller. But this is the trick that we're going to use. So there are these various different controller signals, right? So ALU to mem, read write, all those things. What we are going to do is that we're going to also pipeline these control signals along with data from the data path. So we're going to actually feed this control signals into my pipeline, and I'm going to use them. So think about this, is that your control signals are created at the decode stage. Some of them will be used at the execution, some of them will be used at the memory, and some of them will be used at the write back stage, right? Write back. So what I'm going to do is that I'm going to have 3 separate buffers and then feed this control signals into them. Then once the instruction goes to the execution stage, I'm going to use this, so I no longer need to buffer the control signals relevant to the execution stage, but I still need to buffer the memory and write back, so I'm basically just connect them together. And then at the memory stage, I'm going to use the signals, and then I'm going to buffer the write back, and then here I'm going to use this signal. So essentially, think about this, is that every instruction going to have some control signals generated by the controller when the instruction is being decoded. Now I will carry this information with this instruction as it moves along the data path in the pipeline stages. Goes to the execution, all the control signals goes with it. Some of them will be used during the execution. Then the instruction goes to the memory. I carry all the control signals with it as well. So I'm going to continue carrying the control signals with the instruction itself. This way, I always have my control signals with me. I can actually write them whenever I want to, okay? So this will be the design of my processor with the control signals. As you can see, the controller takes the instruction during the decode stage. Now I'll have a bunch of these wires, and as you can see, some of them will be used. So for example, ALU source, if you remember, was for deciding whether I want to do whether I want to do IM, the immediate versus RS2. So this signal, as you can see, is provided by this pipeline register. It was created at this time in the previous cycle. Now I'm going to use it. So now there's the notion of time. So when I see a signal, in which cycle this signal is going to be used is different. So they're not all within the same cycle. So the complexity of the pipeline design is that you will see different units, but each one is at different clock cycles. Each one is using a separate instruction because now things are parallelized, right? Same story with, for example, ALU operation. But then you will see that, for example, the branch signal is being used in the memory stage, or the mem to read signal is being used at the write back stage. So essentially, I have the exact same control signals that I had before. I'm just using them at different clock cycles. Okay? And again, why we are designing it this way and not, for example, why we don't have this here is, again, because of the delays, because it takes some time for this to be generated and we want this to be balanced. And again, we will see some more concrete timelines as we move forward. Okay? All right. And then as you can see, also, all of your instructions and everything is also being pipelined. So not just the control signals, but your data is also being pipelined. So for example, this is your PC. So your PC is being pipelined and then go through this process. And this was the adder that we were using for PC plus offset. So you can see that this is still PC. So this wire and this wire are exactly the same. We just pass it through the clock cycle so that now since there is like 2 registers in between, the value for this is PC for this instruction versus the value for PC here is PCU for the third instruction. So let me give you an example. Let's say I have a sequence like this. I have add, I have load word, and let's say I have XOR, okay? So my instructions are, so this is instruction number 1, this is instruction number 2, this is instruction number 3, okay? So for this one, PC, let's say, is equal to 100. For this one, PC is equal to 104. And for this one, PC is equal to 108, okay? So what happens in my pipeline is that I initially start with the first instruction inside my pipeline, okay? So if I look at the PC here, the value should be what? Should be equal to 100, okay? In cycle number 1, PC is equal to 100, okay? Now, clock, the next clock cycle comes. So now this instruction goes to this cycle. So let me show you with another color. So now my add will be here, okay? So my add would be here. Now the next instruction that will come to the pipeline will be load word. So my load word would be in this stage, okay? So now if I look in this value here, this is still PC and this is still equal to 100, okay? Because this is the PC of the add instruction. Now it's passed through the pipeline. But if I look at the PC here, this is the PC of the load instruction. This is equal to 104, okay? And then things continue. So now we go to the next cycle. Let's say my next cycle is, let's see if we can find another color. So next cycle, add will be here. Load word will be here. And now we are entering the third instruction, which is the XOR instruction, which will be XOR will be here, okay? So now if I look at the number here, what is the number here? Anyone? 108, right? So PC would be 108 here. What is the PC here? 104. And the PC here, this number, 100. So same wire, 3 different numbers because they're connected to different registers, okay? So don't be confused by that. These are 3 different numbers because each one is pipelined by another buffer. So they're reading from different buffer. This value is coming from this buffer. This value is coming from this buffer. And this value is coming from this register here. That's why there are 3 different numbers, because they're coming from 3 physically separate registers. Same story for every other signal that you see here. So everything that you see here, including, for example, this value here, this value and this value are not the same. This value and this value are not the same. This value. None of these 4 points in my design have the same value, although all of them are technically instructions 7 to 11, which is like find 3, for example, but none of them are actually the value that you're gonna, sorry, this is RD, I think. Yeah, this is RD. None of them are actually the same because there are 4 different instructions in each pipeline stage. Each one has a different RD. Does that make sense? Cool. All right, so there are a whole bunch of like details here. You should look into it to kind of like understand why it works. And again, this should be 32. So you will see different values here. I'm going to go through some of them, but you can pay attention to the rest yourself. So for example, one thing you will notice is that 0 is being pipelined here, and it's coming up here and being used here, okay? Why are we doing this? Because if I want to compute the time for this, right? Remember, I want these times to be almost equal. So this time versus this time versus this time should be almost equal. If I added this AND gate here, the AND gate would be on the critical path for this stage, okay? Versus if I put the AND gate here, now the AND is part of the critical path for this design. And since this is and this are happening in parallel, I'm not really adding anything to the critical path of my memory. So this way, I kind of save some time by moving this from here to here. So I'm reducing the critical path. You can practice this yourself. So consider this AND gate here, and then we will give you numbers and say that, okay, what would be the maximum cycle time for the ALU operation? And then next time you put it here and ask you again, what will be the time for ALU? And you will see that this will be removed from your critical path, okay? But if I want to move this AND gate here, it means that I also moving the branch signal here. So the branch signal is kind of passed through the pipeline to here. And now you will see that this signal is essentially provided back to this PC source here. So this is the register that decides whether I'm taking PC plus offset or whether I'm doing PC plus 4, right? So this signal is available in the mem stage, right? So I know at the memory stage that whether I'm doing PC plus 4 or whether I'm doing PC plus offset. Yeah. The question is, how do you go back in the pipeline? It's not going back. It's just the way that we show this. If I had put this here, then you wouldn't ask this question, right? So it's just a way to make this nice so that people can see. So this is kind of like, so not all the signals from left to right are necessarily in the same timeline, right? So for example, this signal is in the mem stage versus these signals are in the fetch stage. So it's a little bit complicated. And that's why you need to kind of look at these signals and know where they're coming from so that you understand this. Mm-hmm. Yes, this is a problem. So the question is about the branch. And again, this is something that we will run into later. So if my branch is here, basically means that my future instructions are here and they're all PC plus 4, PC plus 4. But if the branch is taken, I basically fetch some instructions that I'm not going to use. This is what we call a control hazard. So we're actually running instructions that we are not supposed to. We're going to show you how we fix this issue. You have to flush them out, basically. So, yeah. We have to reset as well, but we're going to talk about it later. For now, think about no branch. Everything is just PC plus 4, PC plus 4. Yes? Yeah, the question is about that this AND gate is happening in parallel. Yes, remember, still this is hardware, so everything happens in parallel for each stage. So now, for example, this signal, all of these things, like your immediate generation happens in parallel with your register file. So it's still within one stage, everything happens in parallel. Between different stages, there is the clock signal that. But then now what we are doing is that now we are processing multiple instructions at the same time. So I'm processing one instruction here, I'm processing a different instruction here, I'm processing a different instruction here, and so on and so forth. So at any given time, 5 different instructions are being processed, each one also being in process in parallel. So that's maximum amount of parallelization we can have in the system. Yeah. Yeah, so that's a great question. So the question is about writing backs, and that's actually exactly this slide. So as you can see, this point here is your RD, okay? So this is the RD, and as you can see, it's created when the instruction is in the decode stage, okay? And that's exactly what we want. When we read the instruction, we want to see what is the value of the RD, okay? And the second thing that happens is that my register write is also being created at this stage. Whether or not I should write to the register also the control signal for that creates it in the ID, okay? But the actual act of writing happens in the write back stage, right? So that's why I'm passing this through. So as you can see, I'm passing this through the pipeline. So now it goes to the execution stage, now go to the memory stage, and now this value, which is in the write back stage, that's actually the value that is connected to this write register and write data. So I'm reading this value from the write back stage. And again, as you can see, the register write is also coming all the way from here. okay? So as you can follow this, this is actually the signal that's being written, okay? So I created things in the decode stage. 3 cycles later, I'm going to use it back. So, and I'm doing this by just wiring this from the right registers, okay? So if I was really using this directly, so remember in your single cycle, this was directly connected to this one, right? And this will cause issues because I want things from the write back stage happens during write back stage. I want the data from my decode stage happens in the decode stage, right? So that's why these wirings happens this way. And again, you can, for example, follow the other. So like follow this one. This is your PC plus offset that happens during the mem stage. Various different things, right? So this is the value of your ALU results and so on and so forth, okay? Any questions? Great. So this is also, as I said, this is the graphical way of showing this, a little bit less convoluted. So for example, let's say I have 5 instructions, and this x-axis is my time. So this is cycle 1, this is cycle 2, 3, 4, 5, and so on. So what will happen is that, let's say, for example, I have instruction like this. I have an add, then I have a load word, another load word, and another add. What will happen is that I'm going to have something like this. So my add goes into the first cycle into the instruction fetch. Then in the next cycle, my add goes here. Then I can bring my load word here. So if I just look at my second cycle, I'll see that there is an add in the decode stage and there is a load word in the fetch state. Then I go to the third cycle, my add goes here. My load word goes into the decode stage. This next instruction, this another load word comes here. Then in the fourth cycle, my add goes to the mem stage, my load word goes to the ALU stage, the other load word goes to the decode stage, and the final add comes here, and then this one goes here, this one comes here, this one here, and this one here. I don't have any other instruction. That's why I don't have like, we don't continue this here. But if I have like a long list of instructions, then this keeps happening, right? And then at this point, this instruction is done, so there's no more add. The load word goes here, the load word goes here, the add goes here. Then this one is also done, so this load word goes here, this add goes here, this is done, this add goes here, and done, right? So essentially, I'm going to have 6, 7, 8 cycles to finish every instruction. Does that make sense? Any questions? Yeah. Yes, again, the great observation. The question is about this value is being written while this value is being read. And this is going to be a problem that we're going to fix. Good observation. For now, again, don't worry about these things. Let's say we've kind of like magically fixed them. But later, we're going to fix them properly. All right. So there's one very important thing that you're going to see a lot in this course, and this is the part of the hardware design. And this is the idea of what we call half cycle, okay? So the idea of half cycle is kind of, someone already asked this in some other ways, but the idea is this. As you can see, there's this shades here that, that I'm using. The shades is kind of showing that this gray means that that unit is being active, is being used, okay? As you can see, this register file and this register file has different shades. The first one happened kind of at the second half of the cycle. So if this is a full cycle, this is the half of it. And then the writing happens in the first half, okay? So that's what we do intentionally. So essentially, writes to the register happens in the first half cycle of the design. Reads from register happens in the second half of the cycle. Why are we doing this? We are doing this because of scenarios where you want to read and write in the same cycle. So imagine you have something like this, that you're writing to x12, and let's say that this instead of x11 was x12, okay? that question that exactly one of your classmates asked, that if I want to read x12 here, and if I'm writing in the same cycle to x12, now the question is, which value I'm going to read? Am I going to read the new value, or am I going to read the old value? So let's say, for example, x12 was used to be 0, and now after doing this add is equal to 5. So this is my old value, this is my new value, okay? So now the question is that if I'm reading this value here, am I reading 5 or am I reading 0? So 0 or 5. The answer should be, it should be 5, right? Because we are assuming that things happens sequentially. So if I'm doing this, the programmer always assume that older instruction finish first, right? So if I'm running these instructions from the programmer's point of view, we are expecting to read 5, okay? So my hardware design should be such that it always guarantees that we read 5. How do we do that? We use this half cycle idea. So essentially, we always guarantee that the write happens in the first half of the cycle, and the reads happens in the second half of the cycle. This way, at the end of the cycle, we always get the updated value, right? In between, we might get different values, but always in the end, that's when that matters, we get the correct value, okay? This is what the idea of what we call half cycle. As you can see, reads always happens in the half cycle, okay? But writes to the register file happens in the first half cycle. Writes to the memory also happens in the second half cycle because there's some other complications for the memory that we need to fix. But generally, reads should happen. Sorry, this is also read. I made a mistake. So these are all reads. So this is read. This is load word. This is read. This is also read. This is also read. So all the reads happens in the second half cycle, and all the writes happens in the first half cycle. Yeah. Can you repeat the first part of the question? So the question is, if we are making registers out of the flip-flops, how do we really implement this, right? That's your question. So here's what we're going to do, right? So for flip-flops, you have some delays for writing, right? Delay for writing. And let's say that number is x, okay? If that number is x, I'm going to make sure that my clock cycle is bigger than 2x. In this way, I'll always make sure that the write happens in the first half of that clock cycle. And then when I'm reading it for the entire cycle. So I'm not reading it. I start reading from the beginning because this is a combinational logic. But if I open this line long enough, at some point it will get the stable value, right? So if I make sure that my process of readings continues until 2x and my write happens in 1x, then I always make sure that my write is already completed and my read is a continuous and reads from the second half cycle. Does that make sense? Yeah. Correct. Correct. So the question is that this only works, for example, for this particular case between these two guys. But for example, between these two doesn't work. So that's a separate problem. We're going to fix that problem later. But this is more of like, if I happen to read and write to the register file at the same cycle, I'm not going to have any problems because of the half cycle. Yeah. Which final? Yeah, so this one and this one, as you can see, the question is about like this two circles. So this one is write back. So it's writing to the register, okay? So the write happens in the first half cycle. And this one is reading from the register because this is a decode state. So we need to read from RS1 and RS2. So as you can see, it happens in the second half cycle. So write happens first half cycle, read happens second half cycle. Right? Yeah. So if you do read first and then write next, then yeah, you will be messed up completely. So you have to wait one more cycle for this to happen. Yeah. Yes. Yes. Exactly. So the read eventually reads the correct value versus the write is synchronized with clock. So reads typically what we call combinational, which means that it's not really happening with the clock itself. As long as you provide the address at some point with some delays, you can read it. And if the data changes, as long as you keep reading, you're going to read the correct value eventually. Versus write happens with the clock. So as the positive edge comes, then things are triggered. Yeah. So if you're to the memory, so the question is, what if we are writing at the same time, like two different instructions writing to the same register at the same time? So that won't happen, right? So always only one instruction is in the write back. So we don't have multiple instructions in the write back. If we had multiple instructions in the write back, then we also had this additional problem that what if there are two writes happens to the write back? When we have multi-core, we're going to have this problem. And we're going to have what we call load store queue. So there's going to be a queue that writes goes to that queue, and that queue happens sequentially. We're going to talk about that later. But for now, there's only one instruction per cycle. So you're not going to have competition within a cycle. Yeah. So the question is about what? So when it's white, it means that it's not being used. So when it's gray, it means that it's being used, okay? So here, it means that if it's gray, it means that I'm reading during this part. This is also gray. This second part is gray, which means that, again, I'm reading. For example, you'll see that this is completely white because this is an add instruction that doesn't use the memory. That's why it's completely white, which means that I'm not really using memory. But for example, for this load word, you can see that it's gray because I'm reading from the memory. And since it's read, it happens in the second half cycle. So there are two kind of things that you need to remember, right? Reads happens in the second half cycle for the timing. Write happens in the first half cycle. And there are some units that are not being used at some point. So that's why this is the kind of the notation. Yeah. You're talking about these two instructions. Yeah. So the question is about this one. Yeah, ignore this one for now. We're going to get to it. Yeah. Can you say louder? The question is about shaded and not shaded. Shaded means being used, being active. Not shaded means not being used. Okay? Cool. All right, so we have a good recap. Why do I have participation? Okay, let's have a quick break. We're going to come back and talk about the hazards. Okay, so you already asked this, so you kind of know what's going on, but let's actually talk about what we call hazards. So what I showed you was like very kind of simplified assumption that I can feed instruction one by one. There won't be any dependencies between instructions and so on. And then another thing that I did was if things happens at the same cycle, I can fix it. But then we will have scenarios like this, that most of you already pointed out, that I want to read this register, but this register is being written in the previous cycle. And if the time that I want to read is way after the time that way before the time that I want to write, the value I'm going to read is an old value, okay? This is what we call a hazard. So more specifically, consider like maybe a simpler example like this, that these are two back-to-back instructions. This one is RD, so it means that I read x1 and x2, I add them together and I write it to x5. But then in the very next cycle, I want to subtract the value of x5 with x4 and write the results to x20. As I said, from the programmer's point of view, the assumption is that this has to be finished so that this value should be the new value for xy, right? This is the assumptions. And when we are designing the pipeline, we make sure that this happens all the time, right? That's kind of like the main thing for the design. If I put this thing here, you will see that, so if I put the add and sub, in terms of timeline, you will see that the add starts from here, then goes here, goes here, goes here. And at the half cycle of cycle 5, this is when the value of x5 is indeed updated. But if you actually look into the timeline of the sub, you will see that the fetch happens in cycle number 2, the read happens in 3, 4, 5, and 6. And as you can see, the read happens in the second half cycle of cycle 3. So in other words, we are producing the result in first half cycle of 5, but we were supposed to have it ready by cycle 3, right? So there's obviously 2 cycle difference, which means that at this point, the value that x5 is going to read is the old value, which is wrong, right? This is what we call data hazard. This is a problem that we need to fix, and the problem is created by the fact that we are overlapping. So data hazard does not exist in single cycle design. Why? Because in single cycle design, we make sure that this is completed, fully completed, and then we run this next instruction, right? Or in multi-cycle, same story. We put the pipeline stages, but we don't overlap things. But since now I'm overlapping, I need to also be careful about the timing, okay? So this is what we call data hazard, and we need to fix it. Essentially, kind of like to give you a little bit more concrete description of the data hazard is that scenarios that we cannot execute following instructions because of the data dependency. This is what we call hazards, okay? So obviously we need to fix the hazards. And there are various different solutions for fixing the data hazard, okay? We're going to talk about them one by one. Anyone wants to suggest how we can fix this problem? Yeah. So the obvious solution is delaying the sub, right? So don't like switch back to kind of the multi-cycle or single cycle design. Delay the sub so that if I delay, for example, this 3 cycles, so if this happens at this point, then I'm good, right? So if I wait 3 cycles, then I'm going to read the correct value. So the only thing I need to change in this design is that if I delay the next instruction, and of course now the question is, how do I delay? How do I even detect that I need to delay and all those things, which we're going to talk about. But this will immediately fix the problem, okay? But there is a problem with this approach, and that would be wasted cycles. So I'm wasting 3 cycles that I could do something useful that I now couldn't, right? So I need to wait 3 cycles, so effectively I will get the performance hit, right? So I'm going to have a reduction in my performance because now I'm wasting 3 cycles just waiting for the previous instructions. And that's not what we like to do. You have a question? No? Okay. So any other suggestions other than delaying? Yeah. Change the ordering of instructions. So if I manage to put something here that is not dependent on x5, then I can freely run them, right? So if I can somehow change the ordering of instructions that are independent from each other, then I can feed them to the pipeline as is without any problem, okay? Any other suggestions? Yeah. Delay was the first solution. So you can delay. You can either delay or you can find an independent instruction and kind of reorder. These are the two main solutions. There will be a third. Yeah. Kind of same as reordering, yeah. Rewrite the instructions. So if I, for example, this was not X5 and was something else, we would have been fine. But you usually cannot because let's say, think about this as like high level language. So for example, you have something like y is equal to x plus 4, and then you want to have y, I don't know, like array y doing something, right? So y is dependent. You cannot change y to something else. Yeah. We can have a y with a multiplexer. You had the same idea? Okay, yes. So this is what we call a forwarding. So essentially, if I can somehow forward this value back in time, I could fix this problem. And you're going to see that, surprisingly, this value is actually available here, so I can kind of like forward it here. So this is what we call it forwarding. And the beauty of this is that this does not have any performance penalty. You can do it immediately. Okay? So let's talk about these two solutions. So remember, the first one is delaying, or what we call stalling the processor, such that the value becomes ready. That's the simplest, but the slowest. Then you can reorder things, and as long as you kind of figure out the way to reorder, and as long as there are instructions that are reorderable, you can reorder them, then that's also doable. And the third option is what we call forwarding, which is the fastest, but it's the most complex, because now you need to change the entire design of my data path. Okay? All right, so to talk about these hazards, there are actually two types of hazards. We call data hazard, which was the one that I just described, that there's dependency between registers. There's also two other hazards called control hazard and structural hazards. Control hazard is because of the branches and control flow instructions. That's the story of next week that we're going to talk about. And then structural hazard is when your structure, when your, let's say, register file or your ALU and so on are not available to be used. In our design, we're not going to face a structural hazard because we have designed in such a way that everything can be parallelized. But for example, let's assume that your registers can only read one register at a time. That way, if you want to parallelize things, you can, right? We're going to briefly talk about structural hazards, but it's just generally not a big problem in our designs, okay? So let's talk about data hazard first, and that would be the focus of our rest of this lecture. So essentially, data hazard happens when the operands, the data, are not yet available, okay? Because of the dependency to the previous instructions. I gave you an example with the add. So again, as you can see here, you will see that I'm using RD X5, but I'm using RS1 and or RS2, either of these two, doesn't matter which one, it could be both, it could be either. If this happens before this is updated, if these two happens before this is updated, then we're going to have a problem. For X1, we don't have a problem, but for X5, we do have a problem. Okay? This is what we call read after write. Okay? What we call raw data hazard. Okay? So raw data hazard means that we are reading this register after writing. And if the timing is not correct, then we're going to have a wrong value. So that's why we call this a raw data hazard. Okay? So now the question is, how many cycles do we have raw data hazard? Is it 1 cycle, 2 cycles, 3 cycles, 5 cycles? How many cycles do you think we have? Anyone? Yeah. So the answer, one of the answers to anyone, any other answer? Exactly. So it will be 2. So let's see. So look at this example here, right? So we have X5 being written in the first instruction. So that's my RD, that's my write. And I have 2 following reads. I have X5 in the sub instruction, and I have another X5 in this AND instruction. And if I look at the timeline, I'll see that write happens in the first half cycle of cycle 5. And I already told you about sub that needs to be read in the second half cycle of 3. And then if you look at the and will basically happens like this. So this will be your add here, 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 and then sub here, and then your and kind of starts at the 3rd cycle, and then the read happens in the 4th cycle. So essentially, read happens in the second half of the 4th cycle. So it's still too soon, right? So still this is an issue, this is an issue. So both of them, these are raw data hazards. So at least 2 cycles, okay? So now the question is about the 3rd cycle. So let's say I have another add that also use X5. So now the question is, do I have a problem between this instruction here and this instruction here? And again, if you see that the timeline, the sub happens at the 3, and the add happens at the 4, and then this add happens at the 5th. But then, if you remember, I told you about half cycle and told you that write happens at the first half cycle, but reads happens at the second half cycle. As a result, these two does not have any raw data hazards because I update X5 in the first half cycle of cycle 5, but I read X5 in this instruction in the second half cycle of cycle 5, okay? So essentially, at most, I'm going to have 2 instructions that potentially going to have raw data hazards. The 3rd one is being taken care of by half cycle, okay? So as I said, the answer is 2 cycles, okay? Other than raw data hazard, we have 3 other types of combination between reads and writes, okay? So we're going to have what we call write after write, okay, WAW. We're going to have write after read, which we call WAR. And we're going to have read after read, which is RAR, okay? So these are the 3 other ones. Another question is that do we have data hazards in these 3? So the easiest one is the last one. If I have read after read, obviously I don't have any problem because I'm not updating any value. I keep reading these values, right? So there is no data hazard there because no matter when I read it, I always read the same value over and over and over again, okay? But what about write after write? Do I have a hazard for write after write? Why or why not? Yeah. Mm-hmm. Okay, so the answer is depends if one of the second write uses the first write. But why does it matter that if uses the first write? So remember, we're not reading anything. We just, so for example, let's say, let me give you an example here. Let's say I have something like this, add x3, x2, x1, okay? And then at some point, I'm going to have another add that is also x3, but this time, let's say x0 and x4, okay? So in this particular case, we are writing to x3 twice. This is what we call write after write. So do you think that we have a raw data hazard? We have a data hazard here or not? Okay, so if we had x3 as an argument, then we had a problem. But this is backs to the raw data hazard. So we all have a hazard between these two, which is the classic raw data hazard. But now the question is that do we have a problem between these two? And the answer is no, because you just keep writing to the same thing. So as long as I'm following the program's order, as long as I make sure that this happens before this, which in order processor that happens all the time, then I'm good. Okay? So as long as I don't do any sort of reordering of instructions, I'm not going to have a write after write data hazard because I always write to the same register over and over, and then as long as these writes happens in order, then I'm good. Okay? What about write after read? So I'm going to have something like this, that I'm going to have add x3, x2, x1, and then sometime later, let's say I have sub, and then x2, let's say x4 and x5. So I'm going to have a situation when I'm reading, when I'm writing after reading. Is this a problem or not? Anyone? Yeah. Should or shouldn't? Shouldn't be, right? Because again, so here you're reading this, and this happens at decode stage, but this happens at write back stage. So it's way, way after that you're reading things. So again, as long as you're not reordering this, if I put this before the add, then this would have been a problem. But as long as I'm completing instructions, what we call in-order processing, which is what we have learned so far, I'm not going to have any of these issues. So none of these three are actually a problem. The only problem is read after write, which is good news. Yeah. The question is why write after write is not an issue. So again, so this was originally was, let's say x5, right? So essentially the idea is what will happen if I'm trying to write x3 twice, right? Since the final value after these two operations is going to be decided by this, right, was the second instruction, as long as I'm completing these things in order, I'm going to, as long as this happens before this, and then this always guaranteed that it will happen this way because we are executing instructions in order, then at this point, we always have the updated value coming from this instruction. So essentially, the write after write will be only a problematic issue if I somehow reorder these instructions. If I run this add before this add, then I'm going to have this problem. If I'm writing things in order, then I'm not going to have a problem. OK. But then the interesting thing will happen once we start reordering these things. And that's what we're going to actually talk about later in the course. And then you will see that all of these now become a problem. And we're going to find a way to fix them as well. But for now, don't worry about them. So essentially, the only thing that we're going to have is raw data hazard. Every other hazard are not a problem in in-order processors. OK? This is just an explanation of these things that I just said. So right after write, we call this output dependency. And as I said, since the pipelining doesn't reorder any instruction, this is not an issue. Right after read is what we call false dependency. And again, since we are using in-order processor, this is also not an issue. But later, once we have out-of-order execution, both of these things become an issue. And we're going to fix that separately. All right. So let's go back to raw, and then at least now we know that this is the only problem that we are dealing with and we need to fix. We kind of describe how we fix this. The first thing we're going to do is that we stop the processor as soon as we see that there is dependencies. We need to detect that. We need to stop it. OK? So kind of like something like this. So for example, we will have x19 being written here. And as you can see, if my x19, the next time I'm reading x19 is after 3 cycles, because of the half cycle, I can fix this problem. OK? So now the question is, what should I execute between these two instructions? Right? Usually, the thing that we do is that we're inserting what we call a bubble or no op, no instruction, no operations. OK? So essentially, I'm doing nothing, or I'm sending something that has no implications of the system. So think about this. I'm adding, for example, x0 with x0 and x0. This is an example of a no operation. So I'm adding 0 and 0 and writing the result back to 0. Or I'm adding, let's say, x0, x0, x0. Something like that. Something that has no impact on any sort of things in my system. If I essentially rewrite this code and then add that to no-op in there, then I'm going to have the same operation as my original system. Yeah. The question is about the jump instructions. We're going to talk about, so there is what we call control flow hazards for jumps. And that will cause some separate issues. For now, we're not going to talk about it yet, but next time we will. For now, let's assume that everything is kind of nice and linear. Yeah. Great question. So the question is, how do we even know that there is a raw hazard here? And you can do it in assembly, but then then you can kind of insert your no-ops here, but sometimes it might be hard to do that. So in most cases, we actually have a hardware unit to detect that. I'm going to talk about that exactly in the next few slides. All right. So, so what is this bubble and how do we implement this bubble in hardware? So essentially, instead of like feeding this no-op all the way through, we're going to combine this with kind of what we call stalling the processor. So like feeding the bubble into the processor kind of like consume power. And that's not what you want if you want your design to be power efficient. Instead, what you can do is that you can prevent the registers to get updated. In other words, I'm stalling my processor. Think about this as kind of a line of things that going through, like a belt that is going. And I kind of, if I stop the belt, then things are not getting updated to the next register and next registers. The thing about the pipeline, though, is that it's kind of selective. So the thing about pipeline is that you want this instruction to be stalled, okay? You don't want this instruction to go into the pipeline and continue advancing in the pipeline because it doesn't have this value here. But on the other hand, you want this instruction to continue in the pipeline, okay? So your stalling is not like 0 or 1. Some instructions continue and some instructions don't continue. So it's a little bit weird the way that we stall the processor. You want to stall future instructions, but you want to let the old instructions to continue in your pipeline, okay? So let's see how we do that. So we're gonna, as I said, we're gonna achieve stalling by preventing the pipeline registers to being updated. In other words, we are freezing my registers to getting updated, okay? So how do we do that? Let me see if I have the design. I don't have it here. So how do we do that? We essentially kind of do it this way, okay? So if I have my instruction something like this, okay? So if I have my add instruction here and my sub instruction here, I need this to be not going forward, and I need this to go forward, okay? So here's what I'm going to do. So my add is here, right? So my add is here, cycle 1. Then my add goes here. My add goes here. My add goes here. No, actually, let's stop at here, okay? So my sub used to be here, right? So my sub goes here. My sub now is here, okay? Now it's the point that is reading the register. And if we let this sub to continue, we're gonna read an incorrect value, okay? So if, for example, if I just let this to normally go, this would be sub, and this is the wrong value. So here's where stall is happen. So we don't let this sub to move forward. So as you can see, in the next cycle, sub is still in the decode stage, okay? And again, sub in the next cycle is also still in the decode stage. This is the point that now add is in the write back stage. Because of the half cycle, now I can let the sub go. So now the sub goes here and it continues, okay? So now the question is that if my add is here and now add is here, what should go here, right? If I'm not letting sub to continue, I should replace it with something, right? And that's what we call bubble, okay? So essentially, we kind of insert the no-op here, okay? So at this point, my memory stage has add. My ALU stage or execution stage used to be sub, but since sub cannot continue, I replace it with a no-op. And my sub stays in the decode stage, and then the next instruction, whatever it is, like the load word would be here. And now since this cannot continue, this cannot continue either. So this is also frozen. So my load stays here, my sub stays here, and of course I cannot fetch a new instruction here. This is also not happening. And then now my no-op, what used to be in the execution stage, now my add goes from memory stage to the write back stage. So I need to replace the memory stage with something. So my no-op now goes here, okay? Now the another question is that, okay, so the add is here. The add is now in the write back stage. I have one no-op in the memory stage. What should I do in this ALU stage? I'm going to insert another no-op here, okay? And now at this point, my add is done. So now I can let these guys move forward. So my sub is here. Now this no-op goes to this stage. This no-op goes to this stage. And then at this point, now my sub can continue normally. So my sub goes, oh, sorry. Yes, my sub basically goes here and then it continues. Okay? So actually, this should be load. And then so since my sub is now going to the next cycle, here my load word will be here, and then my next instruction would be here. In the next cycle, my sub goes here, my load word goes here, and so on. Let me repeat this one more time so that it might be easier for you to follow, and then I'm going to answer some questions, okay? So originally, I had something like this. My sub was here. Let me actually show you here. Okay, originally I had something like this, okay? 3 instructions next to each other, but because of this hazard, I need to put 2 no-op instructions in between them and then execute the sub instructions, okay? And this, as I said, happens in hardware, okay? So add just continues normally. So this is add, okay? And then at this point, sub was starting here, and then sub goes here, and load word was here, okay? So this is the cycle that things start to change. So up to this point here, nothing changes from the regular pipeline processor. At this point, we realize that, oh, if I want to read the registers from the sub, I cannot because I need to wait until here. So I need to wait 2 cycles for this to happen, okay? So what I'm going to do is that I'm going to prevent this register file, this register here, to get updated, okay? So I prevent the subs to move forward. This is what we call stalling the processor. So stall the decode stage from advancing to the later stage of the pipeline, okay? So, but I don't stall the add because I want the add to reach to this stage here, okay? So I'm going to let the add continue. So add going to continue regularly, but my sub can no longer go forward. So now the question is that add used to be in the ALU stage, now has advanced to the memory stage. I need to replace add with something. I cannot keep add in the ALU stage because then I'll do multiple adds, which also results in wrong values. I need to replace add with some kind of no operation, something that doesn't hurt or doesn't have any impact in my processor. So I'm going to replace add with a no op here. So in regular system that there weren't any dependency, this would have been a sub, but now it's what we call a no-op, okay? So no-op, basically, we let the no-op continues into the pipeline, okay? So the no-op goes in the next stage and next stage. We don't care about no-op because it doesn't do anything. And then again, at this stage, if you look at this cycle here, you still see that sub still is stalled because we need to stall 2 cycles. So again, I'm going to have the same issue. I need to replace this with something. I'm going to put another no-op here, and I'm going to let this no-op to continue. And then at this stage, I'm good to go, right? So my load word was here. I'm good to go, so I'm going to let sub to continue. And then load word was here. Now we can let the load word to continue this way as well, okay? So this will be whatever instruction after load word goes here, and load word kind of continues this way. That make sense? Question? Yeah. So the question is, how do we actually do this in hardware? And that's something that I'm going to talk about later. But it's more of like, so it's kind of detection. So I need to detect that there exists a scenario like this to prevent the sub from moving forward. And then there's another way of what we call inserting the no-ops or inserting the bubbles inside my pipeline. And that's essentially is just inserting zeros into the pipeline. I'm going to show you how we're going to do that. You good? All right. So now the question is that is there any better way of fixing this problem? Because now we are essentially what we are saying is that for every hazard that we have, we're going to have 2 cycles of wasted time, right? So essentially, I'm running these no-op instructions. I'm not letting the pipeline to move forward. And the result, I'm wasting 2 cycles just because that there is a hazard. If hazard was a rare thing, this would have been a big issue. But if hazard happens so often, then I'm going to have a big performance problem because for every single dependency, I'm wasting 2 cycles. So I'm essentially kind of switching back to my single cycle design kind of thing because of these dependencies, which I don't like. Yeah. Yeah. So the question is, how do we actually implement this? And yeah, so as long as you don't let your registers to update it, doesn't matter what you do here. That's why we show it as a no-op, but you can have anything here. As long as you don't update any registers, you can do anything you want into those stages of the pipeline. You just froze. So think about this, that every register, if it has a write enable, you just do the write enable equal to 0, and that effectively means that I can prevent those registers to being updated. Yeah. Great question. So the question is, how do we even know that this happens? Later on, we're going to describe what we call a hazard detection unit. That all it does is exactly this. So essentially, all we need to do is checking the source register with the previous destination register. If these 2 match, we're going to have a problem. Yeah. A question is, can this be done while it's being compiled? Yes, you can. It's just usually the checks would be very, very hard to run all these checks. And again, for stalling the processor, you need to have a hardware mechanism, right? So that's why it's usually done in hardware. But yeah, you can do it in compiler time. The question is why is in compiler is not easy. The compiler can check this, right? But again, as I said, for inserting and continuing this, we need to it's faster to do it in hardware. But again, the reason that we're not doing any of these is that we're going to use forwarding, and I'm going to explain later, which is not going to use any of these. But yeah, you can, if you really want to, you can do it in compiler. Okay, so let me just give you a quick idea about what we call forwarding, and then next week we're gonna, next lecture we're gonna talk about how it works. All right, so here's the idea of forwarding. So what I want to fix is that I don't like the two cycle stalling. It works and it fixes the problem. There's nothing wrong with it, but it means that my performance is not as great as it used to be. Okay. So how can I fix this? I'm going to fix this by somehow forwarding the value of the previous registers to the next registers. Here's what I'm going to do. So if you look at the design of the processor, again, my add is here, my add is here, my add is here, and my add is here, okay? Then my sub goes here, and my sub is here, okay? And this was the problematic time, right? So this is, we need to wait and get the value from here, okay? But here's the interesting observation. The observation is the following. we see that the value that we really need is here, okay? So for add, the output of my register, kind of at the end of this cycle, I have the updated value of x5, okay? So what I'm going to do is I'm going to forward this value from this register. So I'm going to let this register capture this value. In the next cycle, in this cycle, the add goes to the mem stage. The sub was supposed to come to the ALU stage. But here's what I'm going to do. At this point, I'm going to read an incorrect value. So I'm going to basically read old value, garbage. But what I can do is that if I can, what we call forward this value to here, so I'm going to replace these two with the value that I'm reading from this register from the previous instruction, then doesn't matter what I read from the register file, I replace it with the correct value forwarded by the memory stage, okay? So if I have the design here, let me have the design showing you. Yes. So essentially what I'm going to do is that I was reading the register, the data here, right? And this data is old. This is the sub instruction in the decode stage, okay? And these values are old. But in the next cycle, this value is going to go to the execution stage. I'm going to add these two muxes, okay? And then I'm going to forward the value that is generated from the previous stage of the ALU that goes now into this register. I'm going to forward this value back, and I'm going to replace whatever junk I read here by this. Okay? So I'm going to introduce a new mux, which is called what we call forwarding mux, that can decide dynamically whether I want to use the value that I actually read from the register file, which is the case in most cases, or whether I want to replace it with the value from the previous instruction that is now at the memory stage. So I'm going to have a wire connected from the memory stage back to the ALU stage in the execution stage, and I'm going to decide whether or not I want to forward. And my control signal is this forward signal that is generated by this forwarding unit. So I'm going to see whether the condition for forwarding is met. And the condition for forwarding is that if the destination registers of an old instruction is the same as the source register of the new instruction. If this matches, then I'm going to forward, which means that I'm going to replace the value that I read from the register file. I'm going to discard that. I'm going to replace it with the value that's calculated by the ALU, buffered into the execution memory buffer, and then forward this back to here, okay? This is kind of the idea of the forwarding, which next time I'm gonna basically describe it in more details, okay? So essentially the idea would be that we're gonna have scenarios like this, that add can be forwarded from beginning of here to here, and then if I have something like this, I can forward it from the beginning of the write back to the ALU. So I can actually have two forwarding units that either from the memory stage or from the write back stage, I can forward it back to the ALU stage. Yeah. You can have multiple forwardings. You can have multiple forwardings. Yes. Yeah, final question. Yes. You check. I'm going to go through the conditions next time. All right, guys. Thank you.
Ask for the code for participation. I missed that part.
There's no participation.
Oh, okay.
Yeah.
Okay. That was just a slight wrong.
Yeah, from last year. I forgot to